Hello. So today we reached lecture 15. We are still in chapter 18, which is about superposition of waves and standing waves. I'm going to do a quick revision to whatever we covered so far, and then we will continue by solving two problems so as we understand these concepts properly. So, quick revision, standing waves. Standing waves happen whenever waves meet. They should be two identical waves with same amplitude, with same frequency, but they travel in opposite directions in the same medium. Then they will superimpose, that is, they will cause superposition, which produces an oscillation pattern that appears as if there is no motion at all. So we will see something like this, or something like this with the 3 loops or with 5 loops. It will look as if the 5 loops are not moving at all, but in reality, they are moving. So because it appears as if there is no motion, we call them standing waves. And we did the math last time, and we found that y of the resultant standing waves is 2a sine kx cosine omega t. So we see here that this value over here tell us about the position of the places where there is no motion at all. So for example, when x is 0, sine 0 is 0, so there is no motion at all. Okay, and then also for other values of x that we did all the derivation last times, we found that there will be no motion at all. Okay, and these we call them nodes. And the antinodes happen when sine kx is 1. Okay, so then the y resultant will be 2a, and these we call them antinodes. We also found the distance between nodes and nodes. So for example, the distance from one node to another is lambda over 2, and the distance between a node and antinode is lambda over 4. So go back to the previous lectures to see all these things. Another revision, we said, what if we fix the two ends of the string? Okay, so we fix the two ends of the string, and we start two waves which are identical, but they are going in the opposite directions. So there are lots of possibilities to happen. One possibility is that I will only see one antinode. In this case, L, in this case here, L is equal lambda over 2, because the difference between the two nodes is lambda over 2, and it is all of L. The other case is that L is equal to lambda over 2, because there is one lambda over 2 and then another lambda over 2. So in this case, L is equal lambda, or L is a 3 lambda over 2, or L is 4 lambda over 2. Okay, so if I transfer this, I will find that lambda is equal to L, or lambda is equal 2L over 2, or lambda is equal 3 lambda over 2, 2L over 3, okay, or L is equal to L over 4. Okay, so here it is 2L over 1. That is when I see only one node. 2L over 2 when I see two nodes. 2L over 3 when I see 3 nodes, and 2L over 4. Then if I write the frequency, so this is here, we called it lambda 1. This is lambda 1. This is lambda 2. This is lambda 3. This is lambda 4. Okay, the velocity is constant, so I can find F1, which is V over lambda 1. So that will give me 1V over 2L. Here, F2 will give me 2V over 2L. Here, this will give me F3 equal 3V over 2L. And here, F4 will give me 4V over 2L, etc. Okay, so etc. So Fn, we agreed last time, it's equal to N V divided by to L. Okay? And instead of V, we can put square root of T over mu, and this is what we see. And we gave these things names. So F1, we said it is the fundamental or first normal mode. The F2 is second normal mode or second harmonic. The F3 is the third harmonic. F4 is fourth harmonic, etc. And we find that F2 is 2F1, F3 is 3F1, F4 is 4F1. So if I know F1, I can know all the other Fs. Okay. Now, let's do one exercise. So a rope under the tension of 200 Newton is fixed at both ends. So I have the case where there is a rope and it's fixed at both ends. So there are boundary conditions at the two ends. This is a node and this is a node. Okay, they cannot move. Oscillates in a second harmonic. In a second harmonic implies I have two loops. Okay, so second harmonic, I'll try my best to draw it. So I have two loops. Okay, so I cannot make, let me try to make a better one. Okay, so let's assume that this is a perfect drawing. So I have two loops. So I have the tension is equal to 200 Newton. I have second harmonic, so N is equal to 2. The displacement of the rope is given by Y equals 0.05 sine pi x over 2 cosine 12 pi t. Okay, where x equals 0 at one end of the rope, x, etc. Calculate the wavelength. So part A, the wavelength lambda is 2 pi over k, which is 2 pi over k. It's given pi over 2. So this gives me 4 meters. Part A. Second part. L. We are still in A, but now we need to get L. So notice here, L is this distance from here to here. This is L. And L here is how many lambdas? From here to here, remember, from one node to another node is lambda over 2. So this is lambda over 2, and this is another lambda over 2. So L is equal to lambda over 2, implies L is equal to lambda over 2, which is lambda, and this is equal 4 meters. So we found L. Okay, part B. The speed of the wave V. V is equal to omega over k. Omega is given 12 pi divided by pi divided by 2, and this will give 24 meters per second. Just a little bit of math. Okay, C. Thus, the mass of the rope. Here I will be using the formula that V is the square root of tension over mu. Once I get mu, I know the length of the string, which is 4. I calculated in part A. Then I get the mass. So the V is 24, and I'm going to square both sides to get rid of the square root. The tension is 200 divided by mu. So I get mu is equal to 0.347 kilogram per meter. This is mu. And I know that the mass is mu from the formula. Okay, so from the formula, mu is kilogram per meter, so it is mass divided by length. Okay, so the mass is length times mu, which is equal, L, we calculated it, it is 4 times 0.347, and we find the answer 1.388 kilogram. This is part C, and part D, finally, if both the frequency and the linear mass density are kept the same while the tension in the wire is decreased by a factor of 16. Okay, so we decreased the tension by a factor of 16. How many loops are present in the new pattern? Here you just have to remember, or you just have to imagine the case. So now I'm decreasing. If I decrease the tension, I'm gonna see more loops. Okay, if I increase the tension a lot, I will see nothing. The string will just be a straight string. However, if I decrease the tension, remember how I increase the tension or decrease the tension? With standing waves here, there will be some mass, which is, in order, for example, to increase the tension, I will put a very, 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 very high mass. Okay, so a very, 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 very high mass will make the string stretch. I will not see any loops. But here I am decreasing the tension. So I'm gonna see more loops. So let's start by saying F prime is equal to F. But what's the formula for F prime? It's M prime over 2L square root of T prime over mu prime, but mu prime is mu because they said mu prime is also the same. So this is equal to F, which is M over 2L square root of tension over mu. Let's cancel few terms. So the 2L and the 2L cancel out, okay, because they are both. And here there is a mu inside the square root. It cancels out with the mu inside the square root. Now let's continue. Now I have n prime square root of, instead of t prime, I'm going to put t over 16. It's equal to n square root of t. Now there is t inside the square root, t inside the square root. They cancel out, and I will have n prime times the square root of 16 of 1 over 16 is equal to n. Okay, so n prime, what is square root of 1 over 16? It is 1 over 4. So it is 1 over 4 is equal to n, implies n prime equals 4 times n, and this gives 4 times 2 because they were 2 loops, n was 2 in the beginning, and this gives me 8 loops. So indeed, if I decrease the tension, I see more loops. Okay, let's do another exercise. This is the full solution here. So standing wave. So a string of 0.9 meter long. So I have the L 0.9 meter, and I have the density mu is 0.002 kilogram per meter, is fixed at both ends and under a tension of 10 Newton. So tension is 10 Newton. A standing wave is generated along the string as shown in the figure. So we saw this standing waves as shown in the figure. So I have n is equal to 3 because I have 3 waves. Okay. Find the speed of the wave. So we will start by the speed v. The only way to do it here is to use square root of t over mu because I have t and I have mu. And this is equal to square root of 10 over 0.002. And this will give 70.7 meter per second. Okay, part B. What is the harmonic of the standing wave? That is, how much is n here? N is equal to 3 because there are 3 loops. Okay, deduce the wavelength. Here we have to remember that the length L is equal 3 lambda over 2 because it is the third harmonic. Remember, the distance between two notes is 1 lambda over 2. So here I have 1 lambda over 2, 2 lambda over 2, 3 lambda over 2. So 3 lambda over 2 is equal to 0.9. And I get lambda equal 0.6. Okay. Part C, determine the location of the second antinode on the string. So for this, we will come to our drawing again. So we want the location of the second antinode. So this is the second antinode, it's here. And we want its position. So here we have to remember that this distance from here to here is 1 lambda over 2. And then this distance from here to here, from a node to antinode, is lambda over 4. So the position of the second antinode is lambda over 2 plus lambda over 4, which is 0.6 over 2 plus 0.6 over 4, and this gives 0.45 meters. Of course, another way to see it is that it is exactly in the middle of the L, which is 0.9, so it is 0.45. This is part C. Part D. What is the frequency of the string oscillation? Here we have to remember that V is equal to lambda n frequency n, because this lambda and f are dependent on n. Okay, so Fn is equal to V, which we did the calculation, 70.7 divided by lambda n, which is 0.6. So in other words, n is a 3. Okay, f of 3, or let's say lambda 3. F3, that is the third harmonic. Okay, so this is F3 is equal 70.7 divided by 0.6, and this is 117.83 hertz. Part E, write the equation of the standing wave shown in the figure with keeping x and y in meters. And so this is the equation over here. Y resultant is equal. Of course, these things you have to memorize. Okay, I'm just putting them here to assist you. This is equal 2 times A times sine kx times cosine omega t. And this is equal 2 times A. The amplitude from here is 0.2. So 2 times 0.2, this is 0.4. Okay, sine kx, k is 2 pi over lambda times x, cosine omega t is 2 pi times f, and this is here lambda 3, and this is here f3 t. Okay, and now I will just put numbers. Y resultant is equal to 0.4. Sine of 2 pi over lambda is 0.6. This will give 10.47 x. Cosine of 2 pi times 117.83, it will give 740.34 t. Okay, at what times would all elements of the string of the standing wave have 0 displacement? So at what values of t will y be 0? Okay, so we look here, y 0, if I want one cosine omega t is equal, so y is 0 when cosine omega t is equal to 0. And this happens when omega t is equal n pi over 2, where n is equal 1, 3, 5, 7, etc. So this happens at times t equal pi over 2 omega pi over 3 pi over 2 omega 5 pi over 2 omega, etc. Okay, would the energy in the string be equal to 0 at this instance? No. At this instance, the kinetic energy will be maximum, while potential energy is 0. So this you must remember. It happens when y is 0. Okay, so when y is 0, the velocity will be the maximum, the kinetic energy will be maximum, but the potential energy will be 0, so as the total energy will be constant. Okay, so that's the end of today's lecture. Bye.